Okay, so let's do this example. 16.4, 3 charges in a plane. So we have 3 charges. Q1 and Q3 are both positive, and their charge is equal to 1.5 times 10 to the minus 6, and then Q2 is negative, and its charge is equal to negative 1.5, 10 to the minus 6. Let's go ahead and write this stuff down because it's quite a wordy problem. So we use blue for positive. So Q1 has a charge 1.5 times 10 to the minus 6. Q3 is also also positive. My brain just associates blue with negative. Okay, but in this book, red is negative. So Q2 is negative, so its charge is negative 1.5 times 10 to the minus 6. So where are these charges located? Q1 and Q2 are placed at a fixed position, a distance of 6 centimeters apart. So that means that they're on an x-axis or horizontal axis. So Q1 and Q2, Q1 is over here, Q2 is over here, and their distance is 6 centimeters. Okay, I'm gonna go ahead and write that in SI units. 0.06 meters. Q3 is placed at a fixed position, okay, a distance of 4 centimeters above the midpoint of the line that connects Q1 and Q2. So the midpoint of the line that connects Q1 and Q2 is right here, and so 4 centimeters above that would be roughly, I feel like that doesn't look like the middle, would be roughly, right here. And then Q3 is positive, so he's right here. Okay, so here's our arrangement. Okay, so this height is 4. Here's our arrangement. We are asked to calculate the magnitude and direction of the force on Q3 due to Q1 and Q2. Okay, let's label everybody. Q1, Q2, Q3. So we need to find the magnitude and direction of the force on Q3. So before we do any calculating, let's draw a picture of those force vectors, because we can use those simple rules to determine the directions of the force vectors, okay? So we can draw a picture of it first, and maybe that'll help us to do our calculations later on. So remember, the subject is Q3, so we're going to be drawing our force vectors on Q3. And Q3 is going to feel a force due to Q1, and it's going to feel a force due to Q2. So let's tackle the force that Q3 feels due to Q1 first. So Q1 and Q3 are both positive charges, and therefore the force that Q3 feels due to Q1 is going to be a repulsive force. So what direction is that force? Well, it's going to be a straight line directly away. So we're going to draw our straight line connecting Q1 and Q3 and extend that out. And then that force vector is going to point along that line, okay, directly away, because they're both positive. So there's F13 right there. So now what about the force that Q3 feels due to Q2? Well, they're opposite charges, so there's going to be an attractive force. So if we draw our straight line path, that force vector, well, Q3 is going to be attracted to Q2. So its force vector is going to point directly towards, 2, 3, there we go. Okay, it's going to point directly towards Q2, right? Q3 is going to want to move towards Q2. Q3 is going to want to move directly away from 1. So there's our force vectors, okay? So does this look like something, does this help us at all? Well, what we need to do, right, is in order to find the net force direction of Q3, so if we want to find what the total force on Q3 is, we need to add vectors 1, 3, and add vectors 2, 3 together, okay? And so in order to algebraically add the vectors, we're going to need to find the x and the y components of each vector, right? So that we add the x's together and then we add the y's together, and then we get that total force vector. So that's what we're going to do. So the way we're going to do it, so on the slides, there's a method that they do it. I'm going to show you a different method, okay? I think it's cleaner, and it's a little bit less work, okay? It's a little bit more conceptual work, but less written work, all right? So let's draw those components, okay? And so we haven't calculated anything yet. We're still kind of doing prep work here, okay? So we need to find the x and y component of F13 and F23. So I'm going to draw an xy axis right there, okay, with purple, roughly. It should follow that black line. I'll try to, there we go. Okay, and so if we look at the F13 vector, so it's going to have an x component that is parallel to the x-axis, right? So that's going to be F13x. And then it's going to have a y component that goes up and touches the tip of the F13 vector, right? So do we remember that from Physics 1? Okay, and so you might also remember from Physics 1 that vector components form a triangle, right? This is a right triangle here. And so what we're going to do is we need to figure out what are our knowns and what are our unknowns. And do we have enough information? We don't have enough information yet to find F13x and F13y. But we do have enough information to find the hypotenuse of that triangle, F13, right? We can use Coulomb's law to do that. So let's go ahead and find Coulomb's law, because then that's going to bring us closer to being able to find the component. So let's use Coulomb's law to find the magnitude. And what that is going to give us is that's going to give us the hypotenuse of that right triangle, okay? So F13 is going to be K, Q1, Q3 over the distance between 1 and 3 squared. Okay, so K is 8.99 times 10 to the 9 Newton meters squared over Coulomb squared. Just move that down a little bit. Okay, Q1 and Q3, well, they're both positive 1.5 times 10 to the minus 6. So I can just square that term. And then what's the distance between 1 and 3? Well, we're not exactly given that information, but we can figure it out. So we have another triangle, right? In order to find this distance here, we got to look at another triangle, and that's our clue here for what we're going to do after this step. So take a look at this right triangle. This side is 0.03 meters. This side is 0.04 meters. And this side, we can use the Pythagorean theorem to figure out, right? The hypotenuse. Square root of 0.03 plus 0.04. It's going to give us that side. Well, guess what? I don't even need to use my calculator to figure that out, because this is a standard 3, 4, 5 triangle. So that'll save you a bunch of time on standardized tests. You'll see that a lot of times if they give you a triangle, it's going to be some kind of standard triangle, okay, so that you know the angles between, you know the sides pretty quickly without having to reach for your calculator. So so it's a 3, 4, 5 triangle. So that means the distance between Q1 and Q3 is 5 centimeters, okay? So that's going to be 0.05 squared. So we plug that into the calculator, and what we get is, I believe it is 8 point, I thought I had that written down here. Let's go ahead and just calculate it again. So we do 8.99 times 10 to the 9 times 1.5 times 10 to the minus 6 squared divided by 0.05 squared. Yep, 8.09. newtons, right? Newtons, this is the force. So that's the magnitude, right? We didn't include any negative signs. Well, there wasn't any because these are both positive, but we're finding the magnitude, so we wouldn't have included it anyway. So 8.09. So now we have two triangles, okay? And we have some knowns and we have some unknowns. And so I'm gonna put those triangles next to each other. I'm gonna draw them right here. Because what I want you to see is what we have are two similar triangles. Okay, these are two similar triangles. Why are they similar? Well, because these angles are equal. Okay, and you can use some geometry to see that. The geometry being this angle is the same as this one. And since these both bounce off of that purple x-axis right there, then they're equal, okay? There's a couple different ways you can see that, but these are equivalent or similar triangles, not equivalent. They're similar triangles. And so the first triangle is made up of our distances. The second triangle is made up of our forces. So this was 8.09, right? That's the hypotenuse or the magnitude of F13. This is our unknown F13y, and this is our other unknown F13x. Well, now we can use the law of similar triangles to figure out our unknowns, okay? Instead of the other method, which is what the book does, is to resolve it into components using cosines and sines, okay? We can actually completely skip that step. You know why? Because the law of similar triangles states that the ratio of the sides are equal in similar triangles. So, for example, if we define this as our angle, which we don't know, but we know that they're the same, we know that the adjacent over the hypotenuse of triangle 1, okay, is equal to the adjacent over the hypotenuse of triangle 2, all right? And we can do that for all the ratio of all the sides in order to solve for our unknowns. So the first unknown we want to solve for is F13x. And so that's the adjacent side. So for triangle, if we call this triangle 2 and this triangle 1, then we would do 0.03 meters over 0.05 meters equals F13x over the hypotenuse, which is 8.09 newtons. Now we can solve for F13x pretty easily. Okay. And that gives us 4.85 newtons. Okay. Let's do the same thing for F13y. So we'll use the opposite side, opposite over hypotenuse this time. Okay, and that gives us 6.47. Okay, and I think now, if you're looking at the way I'm doing it, and if you're looking at the slides, you can kind of see the equivalence going on. Okay, so let me show you where the equivalence is. What equals adjacent over hypotenuse? That's cosine theta, right? This is the definition of cosine theta. Okay, so what we're seeing is that F13x equals magnitude F13 cosine theta. Okay, this is sine theta. This is the definition of sine theta, right? Opposite over hypotenuse. That's the definition of sine theta. So we are getting what you see in the slides, except we're just completely ignoring cosines and sines. We don't need them, right? They're just an intermediary step that isn't really necessary because we're using the law of similar triangles. So here we go. So what we did is, well, we got half of the problem done, right? We found F13, X and Y. Okay, so let's do the same thing for F23. So let's take a look at F23, find its components, and locate the similar triangle. So I'll use green. So here's our F23. This is our hypotenuse, okay? And you can draw the components. You can draw F23x like this and F23y like this. Or you could even draw them here and here, okay? It might be a little bit more difficult to find the similar triangle if you do it this way, if you do this triangle. So let's do this one. And well, we know, we've already proven to ourselves that this is theta, okay? And this triangle here is, well, I'm going to tell you that this is actually theta as well right here, okay? And the reason for that is because of the fact that, and we haven't proven it, you know, with calculations yet, but the magnitude of F23 is exactly the same as the magnitude of F13. And you can kind of see that because look, Q1 and Q2 and Q1 and Q3, they're all 1.5, right? So when we find the magnitude of F23, it's going to be identical to F13 because the charges are all the same. And number two, because the distances between them are all the same, okay? So because of that fact, this is going to be theta as well. And the second way we know that this here is theta is because if this is theta, then this is 90 minus theta, then this is theta, and this is 90 minus theta, and since this is a right angle, this would be theta as well. Okay, so there's a couple ways you can verify that for yourself. So now we have our two similar triangles, and so let's draw them down here. So we can draw our standard triangle, the one that we're basing everything off of, which has all of our knowns. Okay, we've defined that to be theta. And now we're gonna draw this triangle here, but we need to rotate it. So let's do this. Let's draw it like this. Okay, this is theta, this is our right angle. And this one is F23y, F23x. Let's pick it up. Oops. Let's try it a little more. Okay. Oh, it's all attached to that. That didn't work, did it? I was going to pick it up and bring it down there, but we're just going to have to draw it. Okay, so let's draw it and then we'll rotate it. We'll draw it the way we see it up there. I'm just trying to do it so that it you know, you can visualize it better. Okay, like just to help you guys visualize it better. So this was theta. This is the y, right? F23y, because it's pointing down. F23x, and then this is F23. And then if we pick it up and rotate it, now it's not attached to anything else, to make it look like, oh, we have to flip it, it looks like, right? We got to flip it. So we go like this, and then we can flip it, and you can see that, and these are all legal moves in geometry. I wonder if you can flip it here. Nope, that's not the right button. That's not the right button. All right, what a sidetrack I've gone on, huh? There's no rotate. All right, well, that's something we need to add. So we got to flip it over, but we can just draw that ourselves. Okay, so we're going from here, turning it like this, and then we're flipping it over. So let's copy. Theta would go here. F23 would still be, X would still be on the bottom. F23Y would still be here. And then F23 would still be the hypotenuse, okay? Oops, meant to erase that guy. Okay, so that was a little more difficult to see. Practice makes perfect, all right? So now we can compare. So first we need to figure out what F23 is. We can definitely do that with our Coulomb's law. So we can do that here. And what you'll see is you'll get the same value as F13, and that's because the charges are the same and the distances are the same. Right? The distance is 0.05 meters from 2 to 3, same as 1 to 2, right? The hypotenuse of this triangle, that's the distance. Okay, so you get the same thing as for F13, which is 8.09. All right, so that's 8.09. Now we can set up our similar triangles. So let's do adjacent first. 0.03 meters, 0.05 meters is F23x over 8.09 newtons. Solve for F23x. Okay, 8.09 newtons times 3 over 5. Guess what? It's exactly what we did up here. Okay, so we're going to get 4.85 again. F23y, it's going to end up being exactly the same as up here. Now, what's the difference though, right? Because we're working with triangles here. But when we look at the picture, look at the direct, remember, components of a vector can be positive or negative, okay? Here we're looking at triangles, so everything is kind of like positive looking, okay? But we're using this to find the components of a vector. So when we put it back in the physics problem, okay, we're leaving trigonometry, entering physics. F23y should be negative, right? Because it's pointing down. Everything else will be positive. F13y points up, F13x is to the right, F23x is to the right. F23y must be negative, okay? So F23y must be negative, okay? And that's where my approach, is a little bit different than the approach in the slides. So when you do the cosine and the sines, they put the negative sign in there because they define this theta right here to be negative. This is negative theta because it's rotating down this way versus up this way. And so then that tells you, it clues you in that cosine of a negative theta is negative cosine theta, right? So that's trig. But here, what I'm doing is, this is more conceptual, right? You're using the law of similar triangles, so you're going to have to think conceptually like, hey, this is a triangle, but when I'm plugging this back into my physics problem, I need to make sure that I put my negative signs in the appropriate places, okay? And so that's what we're going to do. So now we're going to basically plug everything into this equation here, okay? So we're going to add F13 vector to F23 vector. And so remember, the way we write these in vector notation is we do F13x, I don't know if you use x hat or I hat to denote the unit vectors. I'll do x hat, okay? And then we're adding that to F123 x hat. And that's going to tell you that you can add the unit vectors, you add like unit vectors. And so let's plug that in. So this was positive, look up here, 4.85. This was positive 6.47. This was positive 4.85. This was negative 6.47. Okay, that's going to give us our total vector. And so, well, we add these up. We add the x's together. Oops. We add the x's together, and they add up to 2 times 4.85, right? Because there's 2 of them. And then the y's plus 647 minus 647. So those go away. So our total, our vector here, total is, total force on 3 due to 1 and 2 is going to be 9. I don't trust my brain right now. 2 times 4.85 is 9.7 newtons in the x hat direction. That is our F3 total. Okay, so the question Calculate the magnitude and direction of the force. Okay, well, magnitude, 9.7 newtons. Okay, direction, to the right, or the x direction, positive x direction. Okay, all right, so that is example 16.4. Okay, we're basically bringing physics 1 vectors back in, but applying the concepts of forces between charged particles.